All right, guys, welcome back. Today's lesson's on erosion, the transport of weathered materials. Now, the primary force that drives all erosion is gravity. Of course, that force is pulling things downhill. It's going to pull broken pieces of rocks, weathered rocks downhill, and that's erosion. Now, first we're going to start off with a form of erosion called mass wasting. This happens just due to gravity, and it's a large-scale erosion. So here's an example, a landslide. Mass movement, you can definitely see why they call it that. Perhaps you've seen this video up on YouTube. It's a landslide in Japan. Now this one happened after a heavy rainstorm. It's very common for landslides to happen after heavy rainstorms. The soil gets obviously heavy and it becomes lubricated, so the ground can give way much easier. Landslides leave a talus slope, which is this angled slope of broken bits of rocks, usually real sharp and angular on the edge. Now, avalanches aren't really a form of mass wasting in a way because it's not sediment and rock that's moving downhill, it's snow, but it's still pretty cool to look at, and it's a lot of stuff moving downhill really fast. Okay, a slower form of mass wasting. This is called soil creep. And it happens when you have a slope on a hillside with soil, and gravity is pulling on that soil. And over time, you can't see it really happen. It just happens really slow. You start to notice things are tilting. In this case, you can see some trees are tilted, some fence posts, some power poles. Looks like a retaining wall is tilted. And all this stuff has to be, if it's man-made, should be fixed over time or else it would collapse. Trees fix themselves. They always want to grow back up towards the sunlight. And you can see on hill slopes how they do that. Now, in addition to mass wasting, there's 4 agents of erosion, 4 things that carry out erosion. And the major erosive agents are running water, that's a biggie, glaciers, which we've just done before vacation, wind, and ocean currents and waves. So for now, we're going to focus on the running water. So some questions. First, what happens to rainfall when it hits Earth? Well, we know rainfall when it hits Earth, some of it can evaporate back up into the sky. You can see that in numbers 1 and 4 in this diagram. Some is absorbed and becomes groundwater. That's occurring right down on the ground level. You can see a bunch of arrows soaking in this area here. All these areas. That's absorption becoming groundwater. But some becomes runoff. So some doesn't soak in and it runs off into the sea. That's runoff. You've seen it around here. Happens after rainstorms or in the spring. All that snow melting. So what determines if rainwater becomes runoff or groundwater? Well, it has to do with the ground itself. So first of all, is the ground wet? Is it saturated? If it is, then water can't soak in anymore and it's going to run off more. Second, is there a lot of vegetation planted or not much at all? Is it like a bare field or is it a parking lot versus a grassy field? Grass tends to slow down runoff. It lets it soak in because the water has to go around all those blades of grass. Whereas, an open field or a parking lot, there's not much to slow that water down. It can really move. Third is the slope, which we call gradient of the land. Once again, it comes down to water speed here. If it rains on a steep slope, it starts moving down that slope. Nothing's slowing it down. It's going to keep running off. If there's something in the way, it can slow it down and perhaps allow it to soak in. So extreme runoff occurs if the ground was saturated with water, had almost no plants, and had a very steep slope. You can see how those 3 factors, the ground is completely full, there's no plants to slow the water down, so it's not going to soak in, and the slope is very steep, so once again, it's moving fast down that steep slope. And then, of course, you could modify all those conditions to make water slow down and soak in, which is what this question is asking. What modifications could you make to this hill to reduce the amount of runoff? And we could pause this here and try to think of some of the things based on the last slide. Okay, moving on. Running water. Most of North America is above sea level. You guys know that. It's obvious. Water flows towards low elevations, eventually reaching the sea. Always wants to get to the sea if it can. Now, when runoff is confined to a channel, streams form. And usually streams form in the areas where it's slightly lower or the rock is a little weaker. And sometimes it's just random. In this diagram to the right, you can see how this is a stream channel and how water speeds are represented here. It's usually fastest flow near the top, just below the surface. There's the least amount of friction there. There's always friction along the edges where the stream channel meets the rock around it, and that slows down the water. And everywhere else it's moving a little bit faster, but the fastest, the least amount of friction is usually in the middle, just below the surface. Okay, watersheds or drainage basins. Now tributaries, you know this is a smaller stream or river that usually feeds a larger one. They contribute to the water is what I learned when I was in school. Tributaries and lands that contribute to the largest stream are called drainage basins. Sometimes we call them watersheds. Now this can be compared to your bathtub. All the water when you take a shower that hits the walls of the bathtub and flows back in ends up going down that drain. That's like a watershed. And if you had a whole bunch of bathtubs all lined up together near each other, all the walls of the bathtubs would separate the other bathtubs. So in nature, there's not bathtubs, but there's mountains and valleys, and those mountains act as drainage divides. They separate one drainage basin from the next, or one watershed to the next. Okay, we're going to skip this. We'll just talk about that later. Now watersheds, like the Continental Divide here and the Appalachian Mountains, these are divides which create watersheds. You can see the largest watershed, the Mississippi River system, in dark gray here. But the Rocky Mountains, which are in this area, and the Appalachians, which are essentially like that, separate the Mississippi River system from other systems. So if it rains in here, it's going to flow eventually out the Mississippi River and to the Gulf of Mexico. However, if it rains over here, it's going to flow out to the Atlantic Ocean, or on this side to the Pacific Ocean. Now, it's a little more complicated up here by the Great Lakes because it can actually here flow out towards the St. Lawrence Seaway and to the Atlantic Ocean way up above Maine. But you get the idea. They're like funnels, funneling the water, whichever way happens to be downhill. New York State has a number of different watersheds and drainage basins. The St. Lawrence, the Champlain St. Lawrence, the Mohawk Hudson, which is what we're in, the Long Island Sound, Susquehanna Chesapeake, the Delaware, the Ontario St. Lawrence system, Erie St. Lawrence system, the Allegheny, Ohio system. So we're funneling water all over the place. Just depends on where it falls, and it's all based on elevations. There's mountain ranges here involved, there's plateaus, there's, just about everything you could think of that could separate water. New York State has a lot of stuff going on as far as topography. Now, one of the things you'll learn from looking at aerial photos, and we're going to do a whole activity on this later, by looking at aerial photos of streams and river drainage patterns, you can often learn more about the geology of the rocks beneath. So for example, if you see this pattern called dendritic drainage, which looks like random branching patterns, you can pretty much be safe to say that the rocks underneath it are somewhat horizontal, and they're equal rock resistance or homogeneous rock strength underneath. And this forms because the water really has no decision to go left or right, or it's just random. And that's what branch patterns are like. You can see like the tree branches, it's a random pattern. Here's an aerial photograph showing this dendritic drainage, this random pattern. And so the rocks in that photograph are pretty much safe to say are horizontally layered and of somewhat equal resistance. Now a different drainage pattern called trellis, this happens when mountains become folded. For instance, when Africa and North America collided, creating the Appalachian Mountains. These folds, where the rocks go up, down, up, down, up, down, funnel water into patterns that look kind of like a trellis, which is a fence in a garden. And you can see on the right-hand side how you have these parallel main streams, and you have these little tributaries coming off the slopes. Sorry, my arrow's not working well, once again, until I get Windows 7. And these streams coming off the slopes correspond to the side view down below. So here's the ridges. Try to write with this thing is weird. The ridges are there, and that corresponds to the side view there. And then here's where the main stream is located, and the little tributaries would be coming off like that. Same thing over here, and your main stream would be right there. So this happens in areas where there's folded mountains. Okay, the third type, radial drainage. This is where streams radiate out like the spokes of a wheel, usually from a central high place like a hill or a volcano. You can definitely see in that photograph on the left how those stream drainage areas in brown are definitely radiating out. And right in the middle there is the peak of that volcano. We're looking down from space here. And the pictures on the right show a top view and then the corresponding side view. And you can see the lines representing the streams flowing out from the top. So this is a pretty simple drainage pattern. Let's move on to a harder one. Annular, like the annual rings of a tree. These are kind of ring-shaped, and it happens when you have usually eroded domed mountains like the Adirondacks or the Black Hills, something where there's different rock resistances but in a semicircular shape. And when it rains there, the water kind of plays like a children's game where you have that little ball and you're tilting the toy to try to get the ball from the center to the outside or the outside to the center. And that's what's going on here. You're trying to get, if it rains, the water, say if it falls there, tries to find whichever way, whichever path is ever going to get it to the bottom. So it's a lot more complicated than a simple radial pattern. All right, now let's practice some of this stuff. The bottom of page 6 of your notes. And until next time, see ya.